So my talk today is going to be a little bit different from the earlier two talks, which I very much enjoyed. I'm going to be talking about risk-benefit from the viewpoint of the public policy person, the planner, the assessor, more than from the viewpoint of the consumer. And this, of course, is my bias as somebody that has worked on the DRIs when they were being set up several years ago. Suzanne Murphy from the University of Hawaii is a collaborator on this. I didn't quite put her name because there's a few slides that are not, that I haven't passed by her yet, and she may still have my height. So I name her, but all right. So okay, this is a disclosure for you. So here's a little bit of an outline for the talk. I'll talk a little bit. So we have, like has been already said before, nutrients are kind of interesting because there's two types of risks, right? When we're talking about nutrition, there's the risk of too little and there's the risk of too much. And so I am going to start discussing the risk of too little only because we know quite a bit about that and we know how to establish thresholds and so on. And then I'm going to try and do a sort of mirror image at the upper intake end. And one of the things I'm claiming is that we do things very differently at the lower end of intake distributions and the upper end of intake distributions, and that there's no good reason to do that. So I'll discuss a little bit the model for developing ULs, the upper tolerable levels. I propose that perhaps we need a new DRI that I had called EAT, E-A-T, but Suzanne pointed out that that meant go ahead and eat some of this. And so we're calling it now the ET, the AT, the average tolerance, so that's not well written there. And I'll talk about this AT to assess populations and to design fortification programs. Alrighty, so let me talk a little bit about risk assessment in nutrition and what we do. So unlike contaminants, like I was saying earlier, nutrients happen to be beneficial if consumed in the right amount. So there's that sweet spot that was mentioned before, where intake is not too little, intake is not too much. And so the two types of risk that we're worried about are the risk of inadequacy and the risk of excess. So what is the risk of inadequacy? Well, we need a certain amount of nutrients in order to maintain our vital functions. And so when the consumption is too low to maintain, is insufficient to maintain the essential functions, we say that the intake is inadequate. And if we have some specific health endpoints in mind, then we more or less know what the average response curve for inadequate intakes is for most nutrients. But most importantly, and this is a statistician in me, we also know that this relationship varies from person to person. So I think that one of the great contributions of the entire DRI process was the definition of distributions of requirements and the formal recognition that requirements are not the same for every person, even if that person is in a single, there's two people in the same life, age and gender group. And so the fact that there's distributions of requirements does provide a framework, the framework that we need in order to assess nutrient intakes from the perspective of the inadequacy. How much do we need? And we do not all need the same amount of a nutrient. And so implicitly, if not explicitly, this dose-response relationship is actually the basis for determining the distribution of requirements. So I suppose everybody's familiar with these concepts, but two of the dietary reference intakes that have to do with adequacy of nutrient intake are the EAR and the RDA. And this is kind of interesting because I am going to be drawing a parallel later on between the UL, which I am going to compare to the RDA, and some other DRI as yet undefined that should be, that is kind of like the mirror image of the EAR. Can you hear me? Yeah, no? Oh, okay. What's the EAR? The EAR is the level of intake. It's the average requirement in a particular life stage group, right? And it's defined as a level of intake that meets the requirements of half of the population for the nutrient. And the RDA is defined as the level of intake that meets the requirements of almost everybody in the population. And I think that these definitions are very unfortunate in that they convey the wrong image. When we talk about the EAR as the level of intake that meets the requirements of 50% of the population, we're thinking, oh my gosh, 50%, if you eat at the EAR, or if we use the EAR for anything, for planning or what have you, we're leaving 50% of the population behind. And that's absolutely not the case. So I like to think of the EAR as the typical requirement. So if I think of a typical person in a life stage group, that person will have a requirement that's around the EAR. Some people may have a little higher, some people may have a little lower requirements, but if you remember what the normal distribution looks like, which is this bell-shaped distribution, most of the persons are going to have a requirement that's around the mean of that distribution by simple statistics. And so let's think about the EAR as the typical requirement in a group. And let's think about the RDA as the requirement of the most sensitive people in this group. So there was this slide today about this one guy saying, yay, among a sea of other people. Okay, that person's requirement is at the RDA. Everybody else's requirement is below that RDA. Okay, and so we should think about those two DRIs in that term. So how do we measure the risk of inadequacy? Well, we know, this is this thing, I think. So to measure the risk of inadequacy, we know what the dose-response relationship is. And so we know what the risk of not consuming enough at different intake levels is under that particular dose-response curve at low intake, at the low intake tail of the distribution. A method that has been around forever, a method that has been around for a long time, since the 1986 NRC, in fact, that's called the probability approach. It's nothing more than that. It's just taking the average of the risks across all individuals in the population, and that risk is given by the dose-response curve that we have for each particular nutrient. In recent years, we have found ways to simplify these calculations, and we have proposed something called the EAR cut point. Beaton was the first person that came up with that idea. I worked on it a little bit more, and essentially what that is the following. So this is kind of an important figure, and some of you have seen it 5 gazillion times, but if you haven't seen it, let me explain it a little bit. So here I have 1,000 invented people. So I have simulated individuals. Each of those black dots is a person. And what I'm saying is that for each one of those people, I happen to know, because somebody told me, I happen to know both the intake and the requirement for the nutrient. Of course, I could never know that. But this is a simulation, so I can know anything I want to. And there's that diagonal line over there. That diagonal line over there is the line along which the requirements are equal to the intake for those people. So everybody that's a black person, every black dot, has intakes that exceed requirements, so those people are okay. And the people that I drew in red at that tail of the distribution are the people for whom intakes do not meet requirements. And so what I would like to know if I am a public policy person is I would like to be able to identify the proportion of red people in my population, right? But in order, so you say, well, just count them. Yes, I can count them, except that that's a simulation, and for those people I know the requirements, and in real life the only thing I see is intake, I don't see requirements. And just looking at people with low intakes is not going to do the trick, because you may notice there's a few people, and I'll mention this person over there, that person happens to have an intake that's lower than the intake of these people over here, yet this person is adequate and these people are inadequate, even though the intake of the bottom person here is higher than the intake of the top red people. That's because that bottom black person has very low requirements, and these red people over here, even though they have higher intake, have very high requirements for the nutrient. And so the trick is, how am I going to do to count the number of reds when all I can see is this axis and I cannot see this axis? Well, it turns out, and this has been shown, that if I count the number of individuals to the left of the EAR line, so if I count the number of people that have intakes below the EAR, that number is approximately equal to the number of people that have intakes below their requirements. So, in other words, just knowing what the intake of my population is, and just knowing what the average requirement in my population happens to be, I can tell you what the proportion of individuals with inadequate intake is in my group. I cannot tell you who has inadequate intake, but I can tell you how many have inadequate intake. And since I'm a public policy person, I suppose, I don't care who's who, I just want to know how many, okay? The RDA is the other line that I drew over here. As you can see, if I were to count how many people have intakes below the RDA, I would be overcounting the people that have inadequate intakes. So the number, So the number of individuals that have intakes to the left of the RDA, it's all those reds plus a bunch of blacks here, all of those are below the RDA, yet many of those do not have inadequate intakes. So using the RDA to assess inadequacy is wrong, and we know it's wrong, and that's what the IOM reports say, and we just don't do it. We use the EAR, which is the average requirement in the population. So there's a mathematical reason to do it. So what's the, this is maybe not, what's the policy implications? Although I'm not talking about policy implications. Well, what we have in mind here when we're looking at inadequacy is we're thinking about a typical person. So we think about a typical person in the back of our minds when we use the EAR to assess inadequacy. And when we plan, if you're planners, we plan for low prevalence. What we're doing is we're planning for a low proportion of intakes below the EAR. If we were to plan for a low proportion of intakes below the RDA, we would be offering too much of the nutrient to the population. In other words, there would be a significant number of individuals whose intake is excessive. So of course the benefit is the same in the sense that everybody would be getting what they need anyway, but there is a risk even on that side, and that's the risk of offering too much. Nutrients come with calories and so on and so forth. So let me now move to the upper tail of the distribution and remind ourselves what the upper tolerable level is. So the UL is defined as the level of intake that is likely to pose no risk for most individuals in the group. So remember how I defined the RDA? It's the level of intake that is likely to exceed the requirements of most persons in the group. So this is not a recommended intake level, so intake levels above the RDA are already excessive for just about everybody. So how do we use the UL currently? Well, we use it as follows. We compare nutrients to the UL, and we say that intakes below the UL are likely to pose no risks, but we don't really know what to say about intakes above the UL. And one reason is that at high doses, we don't know a whole lot about dose-response relationships for most of the nutrients. This is not I'm going to skip that. So the model for setting ULs is the following. And it's a little different for some nutrients, but in general, it's pretty much, this is the way it goes. So first we, of course, find ourselves an adverse endpoint, health endpoint. Then typically using animal studies, we determine either a no L or a low L. And then there's several safety factors or uncertainty factors that are applied to that value before we get to the UL. So first, there's a safety factor to compute the NOL for the low L, if the low L is what we got. There's a safety factor to extrapolate from subchronic exposures to chronic exposures. There's another safety factor that is used to extrapolate from animals to humans. There's another one that extrapolates from one age group to another. And the one that I have written in blue, there's another safety factor that is used to account for differences between persons in a life stage group. So this last safety factor accounts for physiological differences between people. And while this is not explicitly written anywhere, what that is accounting for is different levels of tolerance to high intakes among individuals in a group. So by the time you're done applying all these safety factors, the UL can be quite low. And a typical example, I think we all run into this, is zinc in children, where the UL is very close to the RDA. And you find that if you compute the proportion of children who have excessive consumption of zinc, this is in the order of like 60%. Yet kids are not dying among us, so there's something funny about this number, I think. So here's an example. This is a real example. This is vitamin E, and these are the numbers. These are the published numbers in the vitamin E report, published in 2000 by the IOM. So vitamin E has been linked to hemorrhagic events at very high doses. And using rats, a low L of 500 milligrams per kilogram of body weight per day was established. And so starting from that low L, the UL for vitamin E is set as follows. There's a factor of 2 that's applied to go from the low L to the no L. There's a factor of 2 to go from subchronic to chronic exposure. There's a factor of 3 to extrapolate from the rats to humans. And there's a factor of 3 to extrapolate, to account for between person variability. So within group, between person variability, intolerance to excessive levels of vitamin E. And I'm just talking about adults here. So by the time you multiply all those safety factors together, you get an uncertainty factor of 36. And so the UL is computed as the low L divided by 36, and that gives you 14 milligrams per kilo per day as the UL. And then the committee goes on and multiplies this by an average person, which this is kind of funny. At the time, they use NHANES 3 data. This is 30-year-old data. At the time, the average weight was 70 kilograms. In fact, it was 68.5. Now, of course, we're talking more like 81.5 kilograms for the average person in the United States. But in any event, for a person that weighs 70 kilos, the UL is approximately 1,000 milligrams of alpha-tocopherol per day. All right. So let's conceptualize the UL. So we know how to compute it. We know how it, where it comes from, but let's conceptualize it a little bit. Imagine like as we did on the side of inadequacy, on the side of excess, we now imagine a distribution of tolerances. So even if we look at individuals of the same gender and the same age group and the same physiological state, not everybody has the exact same tolerance to excessive consumption of a particular nutrient. If we imagine that distribution of tolerances, then the UL would correspond to the lower tail of that distribution. So the UL, in fact, is defined as the highest level of intake that is tolerable by almost all members of the population. What do we mean tolerable by almost all members of the population? Well, again, you know, being a statistician, I think of the lower 2.5 percentile, since we think of the RDA as the upper 97.5 percentile of requirements. I'm going to think of the UL as the 2.5 percentile of tolerances. And so what's the conclusion? Most people in the group will tolerate higher exposures. So what we propose then, so here we are. Here we have this kind of inconsistency, right? On the side of inadequacies, we use the average requirement in order to do assessment and to do planning. Yet on the side of excess, we use the lower 2.5% of the distribution of intakes. Shouldn't we be using the average tolerance, thinking about the typical person in the population rather than the most sensitive person in the population? And so what we propose is that we do the same at the upper tail of the distribution that we do at the lower tail of the distribution, and define a new DRI. This new dietary reference intake might be called the average tolerance, the AT. It would be defined for each population subgroup and for each nutrient, like we did for the other DRIs. And then think about a distribution of tolerances in each group, where the variance of that distribution reflects the person-to-person variability in tolerance to excessive exposure. So to establish the AT, what would we do? We would proceed as we do now. We would start We would start with the low L or the no L, and then apply all the safety factors that have been applied, the no L, so the low L to no L, the subchronic to chronic, the extrapolation from animals to humans, but stop there. Do not include a factor that accounts for variability between people. So whatever we know about the variability between individuals is going to determine whether the UL is close to the average tolerance or far from it. So if we expect lots of differences, if we expect that the population is highly variable with respect to tolerance to an exposure, then of course we would expect the UL to be a whole lot smaller than the AT. So let me go back to the vitamin E example. So in the case of vitamin E, again I have my low L of 500 milligrams per kilogram per day. The safety factor that we talked about was 36. But if I eliminate that last safety factor, that factor of 3 that accounted for physiological differences, then, well, this is how I computed the UL. But the AT would then be equal to 42 milligrams per kilogram per day. And that's quite a difference, really. And the reason it's quite a difference is that safety factor that accounts for variability between people is quite large. For most nutrients, the safety factor that accounts for variability between people is less than 3. Sometimes it's 1.5, sometimes it's 2. And it's really interesting. I don't know the mind of the toxicologist, but I imagine that the toxicologist is thinking like a statistician in some sense. A large safety factor means lots of variability across individuals in the group. A small safety factor really means very little variability across individuals in the group. And so we can do all the calculations we want, and I'm not going to go into details. Just look at the last formula over there. Essentially, if I back compute, what this is telling me is that the toxicologist had a coefficient of variability of 33% in mind. Now, those of you that know about distributions of requirements know that the coefficients of variabilities that are implicit in those distributions of requirements for different nutrients vary between about 0.1 to about 0.3. And so this is kind of in the ballpark. So the larger the between person safety factor, the larger the coefficient of variability. And so if you have a safety factor of 1, meaning I assume there's no variability in the population in terms of tolerances, then of course the coefficient of variability would be 0. So the UL would then, 3 minutes, okay. The UL would be a mirror image of the RDA, and therefore I wouldn't use it anymore in order to assess groups or to plan intakes. And the AT would be a mirror to the EAR, and that would be then the DRI that ought to be used for planning and assessing. Here's the figure where I completed. So we know that we all agree on this part of the distribution. This is the distribution of requirements. This is the distribution of intakes, and this would be the new distribution of tolerances that I'm talking about. All right, so in 3 minutes. So then, of course, we would have a mirror to the EAR cut point method, and this would be the AT cut point method. And so we would estimate the proportion of persons with excessive intakes as the proportion of individuals with intakes above the AT for that population. And there you have the figure. Again, we have, these are the true people, these are the true excessive people. And these are the ones that I'm counting as excessive at this moment, everybody above the UL. There's a lot of people here who do not have excessive intakes. Their intakes are well above their tolerances. And so it's much closer if I only count to the right of this blue line. What I'm trying to do is approximate the number or the proportion of red individuals there. So let me skip this. So let me conclude before I totally run out of time. So we have agreement on how to use the EAR to plan intakes and assess inadequacy, but I think we need to rethink what we do at the upper level of the distribution. If we determine excess against the UL, what we're doing is we're being extraordinarily conservative, and we're planning only on account of the most sensitive individuals in the population. An approach that would be consistent with risk assessment at the lower tail would be to use this AT, this average tolerance and distribution of tolerances. For several nutrients, the safety factor has been set to 1. And so in that case, we would set the AT to be equal to the UL because the toxicologists say there's no differences in tolerances. And finally, I thought about using average body weight like is used to set the ULs for many nutrients. It really isn't a good idea. So in vitamin E, for example, we have that the UL is the same for all adult men and women. Well, the 5th percentile of weight for a woman is 50.5 kilos. And so that woman is really, if you use a UL of 1,000 milligrams per day, that woman is really exposed to 20, not exposed, but her implicit UL is 20 milligrams per kilogram per day, which is much higher than 14, the intended. And then a man that weighs 120 kilos, which is the 95th percentile, is really, his implicit UL is only 8 milligrams per kilo per day, which again is much lower than was intended. So there's no good reason to multiply by an average person when in most surveys we actually have the real weight for a person. So I'm done. This is my last slide. This is just something that's being thrown out there, and of course before one does anything more serious, one would have to go back and revisit all the ULs and how every UL has been set for all the nutrients. One would need to think about the policy implications of using an AT for planning, but I can tell you one, and it is that there would be much more room to fortify nutrients, to fortify foods, for example, because we wouldn't be running against a UL that's too low. And for some nutrients, for example, vitamin D, and many others for which we rely on biomarkers, I'm not sure how we would use this model, but one has to think about this. Thank you very much.